Jianxing. He will talk about VST-A, a foundationally sound annotation verifier. Please.
Okay. Hello. Can you hear me? So hi everyone. This is Jianxing. I'm going to talk about our work, VST-A, a foundationally sound annotation verifier. So as you may know, annotation-based verifiers, famous example is definitely. In these verifiers, users will write annotations with the source code of the program to define the specifications and guide the verifier to complete the verification. And another type of verifiers, which is interactive verifiers. An example is VST, which verifies C programs with respect to the computer semantics based on the separation logic. In VST and other interactive verifiers, the source code of the program is usually separated from the specification and the proof of program. So if we compare these two verifiers, we can see that annotation verifiers are generally more automated and convenient to users. And they have a more consistent workflow since users can focus on the source code. Interactive verifiers, on the other hand, require more expertise compared to annotation verifiers. But usually they will have richer assertion languages and the form of proof of soundness. Annotation verifiers are usually first order, and users need to trust some implementations of the verifier, which is less reliable. So what we are doing here is we are trying to bring the benefits of annotated programs to the interactive verifiers. Now I'm going to show an example of demonstrating VST's workflow. So this is source code of a linked list reversal in C with annotations of specifications and assertions. So first, VST-A will parse the program to this control flow graph. We can see here the require is the precondition and the ensure is the post condition. And the assert represents an intermediate state of the program in separation logic. Given this control flow graph, VST-A will find all the paths starting with the precondition or an assertion and ending with the post condition or an assertion. So there will be totally 4 paths for this function. The first path is from the precondition to the assertion. The second path is from the assertion going through the loop to the assertion itself. And the third path is from the assertion to the post condition, which exits the loop. And the last path is from the precondition directly to the post condition without executing this loop. So this is the 4 paths VST-A will generate. The user will need to prove these 4 paths, actually 4 hot triples. And these 4 hot triples, if proved, we will be able to derive the original hot triple of the function that's verify this function. One benefit of this control flow splitting is that if the program is modified or updated, only the proof of affected paths need to be updated. While in typical interactive provers, the whole proof have to be updated. For example, the loop body here will only affect the 2 paths related to the loop. And the post condition will only affect the 2 paths exiting the program. This benefit is more obvious in larger programs. And another prominent feature of VST-A is that it supports non-structural proofs. Structural proofs, which usually using current interactive verifiers, they follow the syntax tree of the program. This is because the goal-directed and tactic level automation is very difficult to go beyond the original whole logic rules, which are mostly syntax theoretic. And non-structural proofs, on the other hand, they do not have to strictly follow the syntax tree. In some cases, this can be a considerable convenience for the users. The first example here of non-structural proof is generalized looping invariants. In whole logic, looping invariants are at a fixed location in the loop, usually at the start of the loop. VST-A relaxes this restriction by allowing invariants to be actually anywhere in the loop, as long as there's no assertion-free loops in the control flow. In fact, the linked list reversal example shown before uses a generalized loop invariant. The invariant is placed after the test of loop condition rather than before the test of loop condition. Though in this example, the generalized loop invariants do not have an obvious advantage over traditional loop invariants. So we can see this example here. This is a program to enumerate a matrix, which is a nested loop. Typically here, we need 2 loop invariants in the verification because there are 2 loops. But if we look at the control flow graph here, actually we can find that only one of them, the invariant is enough. That is the invariant of the inner loop. There's already no assertion-free loop in the control flow if we add the invariant of the inner loop. And this invariant is also sufficient to carry all the information needed. In fact, the outer invariant can be inferred from the inner invariant. We also have an example in our paper showing that the general loop invariant can be more intuitive than loop invariants at the start. That is the operation of red-black trees. The second example of non-structural proof is the omitting join conditions. Like the program on the right, a join condition is needed in Hoare logic if the control flow is joined. Like here, the loop can be executed normally or with break. So here we will need a join condition in Hoare logic. But in some cases, it is more convenient to just follow the control flow of the program and treat them as separate paths. Like in VST-A, we can omit this join condition. This also applies to if branches. Notice that users can still write join condition if they think it's necessary. In summary, we propose a control flow splitting algorithm to generate subgoals from an annotated program. Our approach has three main benefits. The first one is flexibility. Our algorithm is based on the control flow graph rather than the syntax-theoretic Hoare logic rules. This allows more flexibility than applying Hoare logic directly. The second benefit is less proof effort. The subgoals we generated are Hoare triples that only contain the single path of execution. We call that straight-line Hoare triples. These kind of Hoare triples are much easier to prove, and the proof is easier to automate and update if the program is changed. The third point is soundness. Our algorithm is proved to be sound with respect to VST's program logic in C. We are able to prove the functional correctness of the program in original VST. After introducing the features of VST-A, we move on to the implementation details. The core of VST-A is the split function that reduces the functional correctness of a whole program to straight-line Hoare triples. There will be four types of paths in the final results obsolete. The assertion-free path, which directly goes from the precondition to the postcondition without going through any internal assertions. And the head path going from precondition to an internal assertion. The tail path going from the internal assertion to the postcondition, and the full path going between the two internal assertions. The type of split result is shown at the left. The normal, break, and continue in the type means the path is ended normally or with break, continue, or return statement. We don't show the detailed algorithm here. Basically, split is implemented through recursion on the annotated syntax tree. An example here shows that the full path of sequential composition is the union of full paths in both statements and the concatenation of head paths in the first statement and tail paths in the second statement. So with this implementation of split, we prove that the split function is sound. Here's the soundness theorem proof, which basically means the splitted straight-line Hoare triples can imply the original Hoare triple. This theorem is proved by induction over the annotated syntax tree. We'll show the main idea for proof in following slides. It's worth mentioning here that before the soundness proof, that VST supports inversion lemmas. So it's kind of inversion of Hoare logic rules. We show the inversion of sequential composition and if branching here. Inversion lemmas are provable in VST because VST support both deep embedded Hoare logic and high order assertions. Means we can quantify assertions in the assertions. The inversion lemmas are important in the soundness of control flow splitting. Now we'll use the induction step of sequential composition as an example to show our main idea of the proof. In this step, we are going to derive the original Hoare triple, P, C1, C2, Q, from the split path on the right. So first, we can apply the sequential rule to our goal. The sequential rule requires an intermediate assertion R such that P, C1, R, and R, C2, Q. Then we can apply the induction hypothesis. Now we need to find R such that the remaining paths across C1 and C2 are provable. Then we can apply the inversion lemma on the assumptions. In that case, we'll find an appropriate R, which is the conjunction of the weakest preconditions of the following paths. So the proof shown before still remains an important point that worth discussing. If we look at the last step, we'll notice that we need the conjunction rule to complete the soundness proof of sequential compositions. And this is not caused by a proof strategy. In our paper, we give a counterexample showing that the control flow splitting will actually be unsound when the conjunction rule is inadmissible. Though the conjunction rule is provable in traditional horological separation logic, it is not compatible with some extensions like ghost updates, which usually using concurrent verification. That's because the verification of the same program can apply different ghost updates that may be conflicting. So in current state, we don't support ghost updates in VST-A. Another problem related with the conjunction rule is the function calls. Also, calling functions with arbitrary specifications can break the conjunction rule. The reason is similar. The logical variables of specification can have different instantiations in the proof of the same program. We can see this function foo as an example. Here, f is the predicate dependent on the logical variable q, which describing a frame that actually foo doesn't exist. So it's possible to find such f that for two different instantiations of q, the specification is conflicting. So in VST-A, we additionally require all the callee function specification to be precise with respect to this definition. Basically means we are able to unify the two instantiations and preserve the conjunction rule after the call. Traditionally, preciseness is defined on the predicates, like here, while the precise function specification here defined on an operation. In fact, our precise function specification includes some common use cases of precise predicates, like the resource invariants of logs. The definition of precise function specification is also more general than precise predicates in terms of function calls. We believe that most of C functions have specifications that are naturally precise. Non-precise specifications are usually caused by separation logic conjuncts that describe inaccessible memory slices to the function, such as the frame foo here, frame f here in the function foo. And these frames can be removed using the frame rule, like this. It can be removed using frame rule. What's more, the proof of preciseness can be efficiently automated. In fact, all the functions in our evaluation are proved to be precise using our automatic tactics. We can show some screenshots of our artifact here. You can see that they are both one line of tactical proof. Finally, we show our evaluations comparing the proof effort of VST and VST-A. The verified program are in these categories. First, we have some basic arithmetics and operations. Then we have 3 data structures, single linked list, double linked list, and binary search trees. Then we have a slightly larger program, which is a small step style interpreter for a simple imperative language. We can see that for the lines of code metrics, VST-A is generally similar to VST. In some examples, we are significantly better because we can achieve better automation on straight line whole triples. And another benefit that is not obvious in the lines of code is the difficulty of the proof. Given the automatic tactics in VST is already very powerful, we still need a complex structured proof involve dozens of tactics. But in VST-A, for most of the time, you just need to apply full symbolic execution repeatedly, which is much easier than VST. In the future, we can improve VST-A in those directions. We can have better solutions for the conjunction rule. Like we can add annotations for the ghost updates, which allow user to explicitly write ghost commands in the source code in some way. That's we will not have two conflicting ghost updates. And also we can have annotations for function calls. Basically, users can explicitly instantiate logical variables. That's the conjunction rule will be trivial for the function calls. And another improvement can be partial assertions, which users can write partial state about programming instead of full state program, and we can apply the frame rule for them. So thanks for your attention. And
thank you. We can take questions.
Thank you for very nice work. I was wondering, so there was something peculiar about the control flow graph splitting you showed in the beginning, where some code showed up multiple times in the splitting, like the part after the loop, if I saw it correctly.
Yes.
Is that related to the trouble with the conjunction rule? And like, is that really what actual automated verification tools will do? Because it sounds like you are then duplicating work by verifying the same code twice.
Yes, it is exactly corresponding to the omitting join conditions, like here. So if users do not write join conditions, then for soundness, we have to repeat them like in the verification. So if users provide a join condition somewhere, then the following path will not be duplicated.
And if there were join conditions everywhere, would the conjunction trouble disappear?
Yes, but we do not take advantage of that in our proof. Yeah. So if there's only a single path, then yeah, the conjunction rule is definitely like provable.
Okay, interesting. Might have more questions later. Thanks.
Hey, hi, I'm here.
Oh,
hey,
yeah.
Hi. Thank you very much for the talk. If so you're reducing all of this to single paths.
Yes.
Doesn't that risk having a combinatorial explosion in the number of paths?
Yes. This depends on repeatedly on the join conditions. Basically, if users write less annotations, and we will generate more things in the split results. So yes, if you don't want the paths to be duplicated, you can write join conditions for them.
All right. Okay. So there's a user way around this.
Yes.
Okay. Excellent. Thank you.
Okay, more questions? There was a question over there.
Can you speculate at all about how you might support the frame inference?
Sorry. Oh,
Sorry.
can you speak that again?
Can you speculate at all about how you might support something like the frame inference? It seems like the idea of breaking down the verification condition up front before trying to solve anything makes it difficult to figure out what your state is going to look like.
I mean the partial assertion part.
Yeah.
We can support a notations for something you don't want to repeat for the following path, and that doesn't seem like it's like for the following assertions in the same scope, we automatically conjunct a frame for that, and for the following path splitting, that will exactly the same.
Thank you.
Hey, over here, yeah. So it seems that one of the benefits that you would get with this splitting is when you change parts of the code, you only have to redo the proofs for the CFG or the part that is affected by the code. So
Yes.
have you tried measuring how this would improve the performance in this interactive development?
We have some tables shown in our paper, which I don't present here in the presentation. Basically, it's slightly like as I show in this toy example here, this example. So there will be very small changes to only the affected paths have to be updated. Yeah, they are actually in separate verification files. So yeah, so in engineering perspective, we can also speed up the verification time.
Okay.
Okay. Are there more questions?
Remark, the absolute program is wrong.
Sorry?
Okay.
Come back. Once again. No.
Absolute value.
Value program.
Oh, that's the first.
It's wrong.
Yeah.
It's wrong.
It's wrong.
Because you do X is minute and it doesn't work. There was an error in the Java library, so you are not the only one. No?
I don't see where it's wrong.
Yeah, this is probably a typo on the slide, so it's a problem with generating slide code. All right. Okay. Thank you very much for the. We will take other questions offline. Thank you.